What up, math folk? We're going to wrap up our unit on rational equations, and what we're going to do is tackle some of the stereotypical challenging word problems that you see on joking internet memes, and we're going to see how that applies to rational equations, and I'm going to start with this little situation here, because when I watch movies about dream teams of criminals and all that stuff, I always wonder who pays for that. And you have things like Ocean's 11 where they will split a reward at the end, and that's kind of how they get paid. But what about other stuff? So I'm going to set up the situation, and we're going to see if we can use rational equations to figure it out. Okay, so we have this large corporation, BizCorp, and they want to hack into the system of another large corporation, Amerihuge. And BizCorp is going to do this by putting together a dream team of top-notch hackers. And so we got three of them, Comrade, Dark Dante, and Frag, and they're BizCorp. It's going to be BizCorp's dream team. Now, this is where stuff starts getting made up. Let's say each hacker charges about $150,000 per day of work for a job, because if you're hacking into a database, you don't split this pot of gold at the end. You probably have some kind of standard for pay. But I'm just making this up. I have no idea. The question I'm asking is, how much will BizCorp have to pay? And I'm going to start with a situation. What if it takes each hacker individually about 9 days to break into a large system? And there's going to be 3 of them. Okay, so you might figure if all 3 people are working together, how many days would it take for them to break into the system? So each of them takes 9 days alone. They're all 3 going to work together. How long will it take? And you might think intuitively, well, it'll take 9 divided by 3, right? So it'll take 3 days to break into that system. And you might be right, okay? But we're going to prove it how. So you might be thinking, well, 9 divided by 3. And that would be 3 days, because they each take 9 days. But here's how. When you're thinking of something like this, what's going to be super, super helpful is to consider the unit. Okay? Now, what do I mean by consider the unit? You want to consider what each hacker can do in 1 day. Okay? So you want to consider what each hacker can do in 1 day. So in 1 day, right? So you want to consider in 1 day, Comrade can break into a system in 1 day. He can get 1/9 of his job done in 1 day, right? Because it's going to take him 9 days to break into a large system. So for 1 day, he'll get 1/9 of his job done. And the same thing would hold true for Dark Dante. He'll get his job done in 1 day, and then the same thing for Frag. She'll get her job done, or 1/9 of her job done in 1 day. And then we want to figure out, okay, well then, what are we going to have if we add all of them together? What portion of the job would be done in 1 day? Okay, so the total portion of the job done in 1 day. And so we're going to think about that, and then we'll be able to actually solve this equation, right? This is a simple math problem, right? So you had 1/9 plus 1/9, that's 3/9 is equal to x. Okay, so your initial response, 1/3, is equal to the portion of the job done in 1 day. Okay, so 1/3 is the portion of the job done in 1 day. That means if they're all working together, it would take 3 days of work. Okay, so it would take 3 days of work. And since they each charge about $150,000 per day, well, that's $450,000 per person. Okay, so now we're looking at $450,000 per person, and then $450,000 times 3. Okay, so you want to calculate that, you get basically 1.3 million. So you end up spending over $1 million for that particular job. Okay, and that's how we can figure that out. But like I said, intuitively, you could think that it would take 3 days to break into the system because they each work 9, would take alone, it would take them 9 days. But BizCore can't afford to wait 9 days. They need this data now, and so they're gonna have all 3 working together. But how you would consider that is to consider the unit. What would be the portion of the job done in 1 day? And so 1 day, Comrade gets 1/9 of his job done, Dark Dante gets 1/9 of his job done, and Frag gets 1/9 of her job done, and that's what they can get done in 1 day. And so you can figure out what would be the total portion of their job being done in 1 day, and then clearly 3 days of work. Okay, so all this is required thinking. All right, so where things get complicated, though, is what we're saying each hacker takes 9 days. What if we start throwing wrinkles in the situation here, right? What if Comrade takes 9 days by himself, Dark Dante takes 6 days by himself, and Frag takes 8 days by herself? So now we're going to have Comrade's portion in 1 day. Okay, so Comrade's portion in 1 day. Let me spell day correctly. So Comrade's portion in 1 day would be 1/9. Dark Dante's portion in 1 day would be 1/6. And then Frag's portion in 1 day would be 1/8. Okay, so now their portions are different. Okay, so this is what we're going to consider. If we add all of their workloads together, now they're going to work together. How long will it take? Okay, so how long will it take? So we're going to start to figure this out. Okay? So when we figure this out, we can say, okay, well, 1/9 and 1/6 and 1/8, how are we going to add all that up? And now we're going to deal with what we've been dealing with in the unit. Okay, we can clear fractions, we can simplify stuff, we can do all sorts of everything, right? Now, you can look for the least common denominator for all these things. You can do a whole bunch of different methods to solve this. But I think the easiest thing for me is to multiply by the least common denominator. Now, the least common denominator of all 3 numbers happens to be 72. 9 times 8 is 72. And guess what's divisible by 6? 72. So if we multiply all of these by 72, we'll be able to work with a pretty neat bunch of numbers. So we can multiply each by 72. And of course, we multiply all things in the equation by 72, we'll be able to figure it out, right? So 72 divided by 9, of course, gives us 8. 72 divided by 6 gives us 12. And 72 divided by 8 gives us 9. And that's going to be equal to 72 times x, right? And so we can add up all of these. We'll have 29 equaling 72 times x. And then to solve for x, well, all right, that's simple enough. Divide both sides by 72. All right, so 29 divided by 72. That would give us 0.40, basically. But that's all we've given is 0.40. Okay, so that's basically all we're given is that x is 0.40. But that doesn't tell us how many days it would take, right? We have to now start thinking. So remember, we're looking for the unit, right? So x is 0.40. Well, what does that mean? That means x is actually 4/10, okay, because 0.40 is 4/10. But still, that doesn't tell us in 1 day, right? So we need to have a 1 in the numerator, and we have to figure out what that would be for the denominator. This is the hard part. I think what would have to happen right now is I pause, you hit pause, hit rewind, and listen to everything again. We have to figure out what would be the total for 1 day's worth of work. Okay, so we're getting in 0.40, or 1/10 of the day's work. In fact, more accurately would be to set this proportion up from here. 29 over 72 would be 1 over x. We want to keep it as accurate as possible. Okay, so we want to keep it as accurate as possible so we can figure out how many days it would take total. Okay, so this is the hard part. All of this involves thinking. All of this involves thinking carefully and trying to figure out what the situation entails. So we have 29 over 72 is going to equal, well, 1 over x. So now we can cross multiply and divide. So x, as a matter of fact, is 72 divided by 29. Okay, so this is so interesting, right, what just occurred. And you get basically 2.5. So that means it's about 2.5 days is what it's going to take. Okay, so remember what's going on. We're trying to figure out how long it will take. How long will it take? It'll take about 2.5 days. Okay, so now we're at 2.5 days. We can now answer the question. So 2.5 times 150 per day. So we're looking at $375,000 per person. That's per person. Okay, so per hacker. $375,000 per hacker, multiply that by 3, and now you have the total outlay for BizCore. So in this situation, they're paying, again, basically $1.1 million. Okay? So if all three of them work the same amount, we could see how that would work, and if they work different amounts, we could see how that would work. But basically, the most important thing to consider is their portion done in one day. Okay, so that's kind of how this is going to break out, and that's only for one type of word problem. So let's think about some other problems. So here's some things I took from the textbook, which are kind of fun. You'll see in a second. So we're going to figure out how do we do this? Okay, so how do we do this? So we're going to read this situation. In the U.S., 1 out of 60 homes is heated by wood. At this rate, how many homes in the community of 36,000 homes are heated by wood? Now, there should be a variety of questions you start asking. The first of which, why would you call anything with 36,000 homes a community? That's more like a city. That's big. Okay, but anyway, let's start answering the question now. In all of these, here are your notes. In any situation, the first thing you have to do is read and think. What is happening here? And in this particular situation, you know what's happening? You're being given a direct proportion. Okay, so in this situation, you are being given a direct proportion. Not a mixed rate situation like what I opened with, but this is a direct proportion. We're saying 1 out of 60 homes is heated by wood. And so you're talking about a number of homes, and you're talking about being heated by wood. So you're being set a direct proportion. You're talking about a total number of homes, and if it's being heated by wood, okay? So you're giving yourself a direct proportion. So in this one, it's a simple proportion. You have a number of homes being heated by wood. Now, in a simple proportion, you want to set this thing up. So in a simple proportion, you have homes being heated by wood is going to be equal to, because it's a direct and simple proportion, another certain number of homes and another certain number of homes being heated by wood. Okay, so you can set up a proportion that looks just like this, and there's other ways. There are other proportions you can set up, but this is like the first thing I'm thinking of. We're comparing homes, the total number of homes, compared to the number of homes heated by wood. So once you set up your direct or simple proportion, now we can cross multiply and solve, but we have to start inputting numbers. So how do we set it up, right? So the way we set this proportion up is we look for the standard being given. What is the standard number of homes being heated by wood? And it tells us right in the problem. It's saying 1 out of 60 homes. That means there are 60 total homes. One of them is going to be heated by wood. And that's how we can set this up. And as I've said before, it can be flipped, it can be turned around. There's many different ways to set this up. But as I'm setting this up, this is how I'm interpreting it. You can interpret it differently and still be correct. So we have the total number of homes is 60, and then every one of them is going to be heated by wood. So if I'm setting up the proportion, I'm looking at it this way. This would be my original proportion, or my original ratio. Now, the second, what I'm comparing it to is the question. At this rate, how many homes in a community of 36,000 are going to be heated by wood? So the question is, how many are heated by wood? How many heated by wood? That's actually the question. And once you have identified the question, you have identified the variable. And once you've identified the variable, you have an equation. So heated by wood is the question. Therefore, that is our variable. Ta-da! And we can set this proportion up. And it's saying, well, out of 36,000 homes. So we have now set up our proportion. So when I say set it up, that's what we've done. We go back to read, and we figure out where things belong, and now we're good, right? So now we cross multiply and solve. Okay, so we can cross multiply 60 times x and 1 times 36,000, and then you divide both sides by 60, and then you can come up with your result. Now this is what I'm going to do, is divide by 60. It's 600, right? So x is 600. 6 goes into 36 6 times, 2 more zeros. But you can use your calculator for that. So x is 600. Now before you start circling stuff, you always want to make sure that you're answering the question. So always answer the question. What was the question? At this rate, how many homes are heated by wood? So if there's 36,000 homes, 600 are going to be heated by wood. That sounds about right. Okay, so do a common sense check. Make sure your work is fine. Common sense check, make sure your work is fine, and then you're going to be done. Then you're set to answer the question. So don't just say, well, 600. 600 what? So 600 homes are heated by wood. That's the answer. So what's our solution? Well, there's going to be 600 homes. That's what you're going to circle. That's going to be your result because you've done the common sense check. It makes total sense, and you're answering the question. All right, so sometimes you may come across a word problem that is a simple proportion, direct proportion, sometimes. Now, what about in another thing? So here's another example, again, taken from the book. My friend Greg can paint a room in 3 hours by himself. His brother Phil can do the same job in 5 hours by himself. How long would it take them to paint that room if they work together? This kind of sounds like the opening problem with my hackers, right? Kind of sounds like that. But you have to read through it and think what is going on. So the first thing you're going to do is read and think. What is going on? So you're thinking through it. I got one guy with one rate and this other person with another rate. What's happening if they work together? It's called a mixed rate problem. So what's happening is a mixed rate. Okay, so this is very much like the opening. Now, how is it that we attack a mixed rate problem? The same way we did in the opening. We have to break it down by units, and I call it a little 1 over. It means the question is, what would be the portion of the job done in 1 unit? Okay, so the portion done in 1 unit is what we have to think. So if Greg can paint a room by him in 3 hours by himself, the question is, what portion of his job can be done in 1 hour? Okay, so we got to think, what portion of the job can Greg do in 1 hour? He can finish his job in 1 hour. He can finish 1/3 of his job in 1 hour. We have to think of the unit. Okay, so that the units are basically the common thing. So Greg can get 1/3 of his job done in 1 hour. His brother Phil can get the job done in 1 hour. He can get 1/5 of his job done. So Phil, 1/5 of his job is done in 1 hour. What happens if they work together? Boom, boom. Okay, so what happens if they work together? Now, in the original opening, we had to do a couple of things, right? We had to think of it by unit. Well, we want to think, well, how much of their job can they get done in 1 hour if they're working together? That's what we don't know, right? So we want to look for the total unit. What would be, if they're working together, how much of the job would they get done in 1 hour? Okay, so now you're looking at the total as they're working together. How much of their job would they get done in 1 hour if they're working together? Okay, so we break it down by unit equals 1 over x, right? This is my last little note for you. And so the rest is get it done, right? The rest is solve the equation. We can use these rational equations. So in this case, we're reading and thinking. We find out it's mixed rates, all right? So now we add these two fractions, a third and a fifth. Let's multiply everything by 15, right? If we multiply everything by a common denominator, we're going to be all set. Okay, so we multiply everything by a common denominator. We're going to be all set. 15 divided by 3 is 5. 15 divided by 5 is 3. And then we'd be left with 15 over x. And so we can now solve, right? 5 plus 3 is 8. 8 equals 15 over x. Let's cross multiply or clear the fraction, either way. So we'd have 8 times x on one side. What would be on the other side? 15 times what, right? 15 times 1, believe it or not. And so we have 8x equaling 15. We divide both sides by 8. And so we have basically almost 2, right? So 15 divided by 8 is almost 2. I'm actually punching stuff in. So it's 1.875. Close to 1.9. Okay, so if we're going to break it down by unit, how long would it take them? Basically 1 7/8 of an hour. So that's how long it would take. It would take 1 7/8 of an hour. Or 1.875 hours. Okay, so that's how long. Almost 2 hours. That's the question, right? So how long would it take them to paint that room if they work together? And we want to do that common sense check. Does that make sense? Yeah. This guy can do it in 3, he can do it in 5 together. Yeah, 1 7/8 of an hour. That's about right. It seems about right. Okay. So that's how we would approach a problem like that. Now I'm going to give you one more example, because this is going to be some fun stuff here. Now, a fisherman traveling on the Pearl River takes 2/3 times as long to travel 60 miles downstream in his boat than to return. If the boat's speed is 25 miles per hour in still water, find the speed of the current. Like, holy cow, what is going on here? So we're going to read and think. I just keep seeing distance and speed, and there's find the speed. There's times long, right? So there's time and distance and speed. Something should be sticking out at you. We're going to read and think. And the thing that should be popping out at you is a famous equation: distance equals rate times time. Okay, so, or y equals mx. What? Okay, so distance equals rate times time. This is what's going on. In this situation, we're dealing with a distance, rate, and time problem, but it is crazy. So I call it an affected distance equals rate times time problem. I call it an affected one because we have to think about what is going on. We have two situations. We got downstream and upstream. Okay? Now the cool thing here is that the distance remains the same. So the distance downstream is the same as the distance upstream, which is 60 miles. Okay? So in this particular situation, the distance is remaining the same. It's 60 miles. So we're reading for that. The distance remains the same. It's 60 miles. The only difference is we have downstream versus upstream. So now we have to read to think what's going on. So here's a couple notes that you want to think. Whenever you're dealing with upstream or a headwind or something that's making things slower, we're going to end up subtracting something you'll see in a second. So when we read downstream, upstream, downstream means it's going faster. The current's making it go faster. You might experience a word problem that has something to do with headwind or tailwind. It's the same type of thing. Headwind is what you're pushing against. Tailwind is what's helping you. Okay, so when it comes to speeds, headwind and upstream, they're slower speeds. So we're going to end up subtracting a speed. Tailwind and downstream, they're faster. We're going to end up adding a speed. Okay. So now, what do I mean by affected distance equals rate times time? Well, we know it's 60 miles, and we know we're going to be dealing with upstream and downstream. Okay, so we're going to be dealing with upstream and downstream. Okay, so 60 miles remains the same. What's happening upstream? We go back to reading. Remember, read and think. Fisherman traveling takes 2/3 times as long to travel 60 miles downstream. Okay, so it's taking him 2 times as long to travel 60 miles downstream. Doesn't that mean it's faster to go downstream because it takes less time to go downstream? Yes. Okay, so it's 2/3 time to go downstream. True. So no matter what the time is for upstream, the time downstream is going to be 2/3 that amount of time. Okay, this is what we're reading. We're reading and thinking. The time upstream, whatever it is, it's going to be 2/3 that to go downstream. Now, if the boat's speed is 25 miles an hour in still water, okay, so all sitting by itself in still water, the boat's 25 miles an hour. How fast will that boat go upstream? Okay, now the rate is going to be affected because it's going upstream. And upstream means we're going to be subtracting the speed of the current. So no matter how fast that boat is, it's going to be slower by the speed of the current. And we don't know what the speed of the current is. So we're going to call it 25 minus R because it's going slower upstream. It's going slower upstream. So whatever the boat is in still water, it's going to be slower going upstream. Whatever the boat is, it's going to be going faster downstream. Okay, so for the downstream, we're going to have 25 plus R because downstream goes quicker, goes faster. Okay, so here's the deal. We have now a system of equations. We have now a system of equations because here's this equation now. We have 60 equals T times 25 minus R. And then here we have 60 equals 2/3 T times 25 plus R. We now have a system of equations. Okay, so that means we can solve one for one variable and then solve for the other variable. Okay, so this is what's going on. So let's simplify our system of equations. So we now have a system. Let's do some work. Okay, so in the upstream system, 60 equals 25T minus TR. In the other equation, we would have 60 equals 2/3 T times 25 plus R. Okay, and now we can start figuring stuff out. You know what I could have done in this first system is to solve for T right away. If I had solved for T right away, I would find it easier. So let me not do that, and let me solve for T right away by dividing both sides by 25 minus R. So the T for upstream is 60 divided by 25 minus R. That's my T. And then I'll be able to find out what R is. Okay? So this is a little bit complicated, I know, but once we think, the rest is work. Okay? Once we think, the rest is work. The biggest thing is upstream, downstream, system of equations, get one of the variables by itself. So now I'm going to finish this bad boy. Now I'm going to plug it into my equation for downstream. 2/3 of T, but now we know it's 2/3 of 60 divided by 25 minus R. All of that times 25 plus R. Now look at that. I want you to stare at that equation, and it's going to get nuts. So let's work this out together. Because remember, as long as we are clearing fractions and doing everything, it'll all work out. All right. So we have this crazy equation. Let's solve. Let's solve for R. The first thing I'm going to do is clear fractions. Okay, so I just want to, or maybe let me just simplify everything. So I'll do that first. So in the numerators, I have 2 times 60 times 25 plus R. In the denominator, I have 3 times 25 minus R. Okay, so I've simplifying a little bit. Let me simplify a little bit more. 60 would be 120 times 25 plus R. In the denominator, 3 times 25 minus R. All right. So I've simplified a little bit. And now I'm going to cross multiply and call it a day. So I'd have 60 times 3 times 25 minus R. And that would be equal to 120 times 25 plus R. Okay, so all this crazy stuff is going on. The rest is just multiplying out. I'm going to do this slow. 60 times 3, 180. 25 minus R. And then I can start simplifying the right-hand side as well. 120 times 25, 3,000, plus 120R. Now I can simplify the left-hand side. 180 times 25, 4,500, minus 180R. See, now we're ready to solve for R. See, now we can undo stuff. Let's add 180R on both sides. And watch this. At the same time, I'm going to subtract 3,000 on both sides. So I'd have 1,500 on the left-hand side, and then 300 on the right-hand side. Divide both sides by 300. Zeros cancel. R equals 5. So all of that crazy, crazy stuff, R turns out to be equal to 5. All right? Now, before we go circling answers, remember we want a common sense check. Does this make sense? Would R be 5? Well, what was the question? What's the speed of the current? Does 5 miles an hour make sense? Yeah, a boat going 25 miles an hour in still water, a current being 5 miles an hour, totally makes sense. So the answer to the question, 5 miles an hour. Crazy stuff. The common theme to all of these word problems, reading and thinking, reading and thinking, reading and thinking. So enjoy. I'm done. Peace out.